everyone, thank you so much for clicking onto this video. Here are today's learning objectives. So we're first going to look at calculations using amount of substance in moles involving mass, gas volume and solution volume and concentration. And then we're going to look at the ideal gas equation. We're then going to look at the use of stoichiometric relationships in calculations. And then finally we're going to look at a required practical, which is the determination of moles. So now we're going to look at concentration. So concentration is a measure of how much solid we have dissolved in a certain volume. And if a solution contains more solid dissolved in a particular volume, then we say that it's more concentrated. And so its concentration value will be higher. And we measure concentration in moles per decimeters cubed. So that's the units of concentration. And this basically means how many moles we have dissolved in 1 decimeters cubed, which is the unit of volume. And a solution of 1 mole per decimeters cubed means that there is 1 mole of a solid dissolved in 1 decimeters cubed. So for example, to make 1 decimeters cubed of 1 mole per decimeters cubed of sodium chloride, we would need to dissolve 58.5 grams of sodium chloride in 1 decimeters cubed of solution. And how we know this is that this is the amount of grams in 1 mole of sodium chloride. So this is the mass of 1 mole of sodium chloride, because we know that because the concentration of the solution is this 1 moles per decimeters cubed, this is the concentration. That means we have to have 1 mole of sodium chloride dissolved in this solution. And so we need the mass of that 1 mole, which is 58.5 grams, which is the molar mass. Now we're going to look at 2 mole equations that we need to use in calculations. So the first one is that the number of moles of a substance is found by dividing the mass of the substance by the molar mass. And this mass has to be measured in grams, because this molar mass we measure in grams per mole. And so that's why the mass of the substance has to be in grams. And this also makes sense because the molar mass, the definition, is the mass of 1 mole. And so if we divide the mass by the mass of 1 mole of that substance, then we should be able to find the number of moles that we have of that substance. And then the second equation is also to find the number of moles of a substance. But this time, we use this equation if we're given the concentration and the volume instead of the mass and the molar mass. So the number of moles of a substance is also equal to the concentration of a substance multiplied by the volume of a substance. And this time what we have is that this concentration has to be in moles per decimeters cubed. And the volume of the substance is therefore measured in decimeters cubed. And in order to convert from centimeters cubed to decimeters cubed, so usually in questions, they'll give you the volume in centimeters cubed, because that's how they normally, that's the unit they normally use for beakers, for example. And so we have to divide it by 1,000 or multiply by 10 to the minus 3. And if we were told the volume in meters cubed, then we need to multiply it by 1,000 to get to decimeters cubed. So multiply by 10 to the power of 3. And so we can see that centimeters cubed is the smallest unit, and then followed by decimeters cubed, and then meters cubed is the largest. And if we look more into the units of this equation, we can see why we have this equation, because the units of number of moles is just moles. And then the units of concentration is moles over decimeters cubed. And then we have the volume, which is measured in decimeters cubed. And so these two then cancel out, and so we end up with moles. So now we're going to look at some mole calculations. So firstly, we're going to try and work out the mass of water needed to convert 28 grams of calcium oxide to calcium hydroxide. So the first thing we need to do with these questions is to write down the chemical equation. So we have calcium oxide, which is CaO, and then we're adding some water, and we're going to form calcium hydroxide. And now we need to check if the equation's balanced, which it is. So this is our chemical equation. And then what I like to do is just write down what I have of everything. And so basically everything that's given to us in the question. So we're told that we have 28 grams of this calcium oxide and nothing else. And so now what we do is we work with this 28 grams of calcium oxide. So what we can do with it is to find the number of moles that we have. So the moles of calcium oxide is equal to the mass divided by the molar mass. So we have the mass is 28, and then the molar mass is the relative atomic mass of calcium added with the relative atomic mass of oxygen. And so we have 40.1 plus 16.0, and this is equal to 0.499 moles. And now we use our equation to compare the ratio of all of our substances. So we have that we have 0.499 moles of calcium oxide, and from equation, one mole of this calcium oxide reacts with 1 mole of water. So we compare it to the thing that we're trying to find. So in this case, that's the water. And so what this tells us is that 0.499 moles of calcium oxide will react with 0.499 moles of water. So now we can use our mole equation, but rearranged, to find the mass of water that we reacted this calcium oxide with. So our third step is to rearrange the moles equation. So we have moles is equal to the mass over the MR. And so if we rearrange this, we get the mass is equal to moles multiplied by the MR. And so we can find the mass of water. So the mass of water is equal to the moles of water, which is 0.499, and then multiplied by the MR of water, which is 1.0 plus 1.0 because of the two hydrogens, and then 16 for the oxygen. And so this gives us 8.98 grams. And so 8.98 grams of water was needed to react with 28 grams of calcium oxide. So for this second example, we're going to calculate the mass of sulfuric acid needed to make 500 centimeters cubed of a solution of concentration 0.5 moles per decimeters cubed. And so firstly what we do is we have a look at how many moles of sulfuric acid we'll need to make this solution. So we have that the moles of sulfuric acid needed is equal to the concentration of the solution multiplied by the volume of the solution. So we have concentration multiplied by the volume, which is in decimeters cubed. So that gives us 0.5 multiplied by 500 centimeters cubed. And remember, to convert from centimeters cubed to decimeters cubed, we have to divide by 1,000, or we multiply by 10 to the power of minus 3. And so this gives us 0.25 moles. And so now we can work out our mass required, because we can rearrange the mass, moles, and molar mass equation. So we have that the moles is equal to the mass over the MR, and so that gives us mass equals moles multiplied by MR. So we have that the mass of sulfuric acid, which will be needed, is equal to 0.25 multiplied by the MR of sulfuric acid, which is 1.0 plus 1.0 plus 32.1 for the sulfur, and then plus 4 times 16 for the oxygens. And so this gives us 24.53 grams. And now we're going to look at moles of gas. So gases are usually really light, so basically they have a very low density. And this makes it very difficult to weigh them in the same way as we weigh solids, so with a balance. And so when we want to know how many moles of the gas are present, we can use the volume instead of the mass. And the general rule that we have is that 1 mole of any gas at room temperature and pressure occupies 24 decimeters cubed. And we saw how we could get this from the ideal gas equation. So if you look back to the ideal gas equation video, then you'll be able to see how we found this 24 decimeters cubed. And so we can form this equation: moles of gas is equal to the volume of the gas in decimeters cubed divided by 24 decimeters cubed. And actually, if you wanted to work it out in centimeters cubed, that would be fine also, because it's just a ratio. But you have to make sure that both the units of the top and bottom of this fraction are the same. And to remind you of the conversions, we have that 24 decimeters cubed is equal to 24,000 centimeters cubed, and it's also equal, and it's 0.024 meters cubed, because we have to divide by 1,000 to get to meters cubed. And one really useful one to know is actually that 24 decimeters cubed is also equal to 24 litres. So we have that 1 decimeters cubed is equal to 1 litre. And so, for example, we're going to work out the volume that 8 grams of oxygen gas will occupy at room temperature and pressure. So the general rule that we have here, we have to remember that this is at room temperature and pressure. And so those are the only conditions where 1 mole of any gas will occupy 24 decimeters cubed. So what we need to do here is to work out how many moles of this oxygen gas we have. And so then we can work out what the volume is. So we have that the moles of oxygen is equal to the mass over the molar mass. So we have 8 over the molar mass of oxygen, which is 2 times 16.0. And so this gives us 0.25 moles. And so we must have a quarter of this 24 decimeters cubed, because we only have 0.25 moles. We don't have 1 mole. And so to find the volume of the gas in decimeters cubed, we rearrange this equation that we have with the moles of gas and the 24 decimeters cubed. So it would be 0.25 times by 24, and this equals 6 decimeters cubed. Now we're going to talk about the ideal gas equation. So the main point about gases is that the volume of a given mass of gas is never fixed, because it can change with pressure or temperature. So the ideal gas equation looks at the relationship between volume, pressure, and temperature. And we actually have 3 gas laws which show the relationships between volume and pressure and temperature. So first we have Boyle's law, and he stated that the volume of a fixed mass of gas is inversely proportional to the pressure. And this is provided the temperature is constant. So we always have the third thing, because then we know it won't affect it. So how we can write this is that we can say, if we denote the volume with a capital V, that means that V is inversely proportional to the pressure. So we write 1 over P. And so we can form an equation where we have a constant. So V is equal to a constant K divided by P. So that is the equation that we form. This is where K is a constant. And then we have Charles' law, and he stated that the volume of a fixed mass of gas is directly proportional to its temperature. So Boyle's law was all to do with volume and pressure, and Charles's law is to do with volume and temperature. But this time the temperature is directly proportional to the volume. And this is provided the third thing is constant, so the pressure is constant. So going back to Boyle's law, what we had was that if the volume was doubled, for example, the pressure would be halved. So that's what we call inversely proportional. However, when we say directly proportional, we say that it's basically if the volume doubles, then the temperature will also double. So it'll follow exactly the same thing as what the volume has done. So we write that the volume, and this is a proportional symbol, and if we denote temperature with a capital T, this is what we would get. And so again, we can form an equation where we have V equals a constant multiplied by the temperature. So we no longer have this proportional symbol, and we can actually form an equation. So this is again where K is constant. Which means it never changes for any volume or any temperature. And so the third gas law we have is Guy-Lussac's law. And he stated that the pressure for a fixed mass of gas is directly proportional to its temperature, provided the volume is constant. So this time we have that the pressure is directly proportional to the temperature. So we can write this as a capital P and then the proportional symbol and then a capital T. And so again, we can form an equation where we have P is equal to a constant multiplied by the temperature. And this is again where K is constant. And so if we combine all of these equations together, we form this ideal gas equation. So the ideal gas equation is PV equals nRT. And now we're going to see what all of these letters mean. So firstly, we have pressure. And then we have big V, which is volume. So these are all to do with gases. So the pressure of a gas, the volume of a gas. And then we have N, which is a number of moles of the gas that we have. And then R is actually a constant. So this is what we call the gas constant. And this is given to us in questions. It's about 8.31 joules per Kelvin per mole. And then finally we have big T, which is the temperature. So now I'm going to go through the units, and it's really, really important that you remember what all of these are measured in, because the questions will really likely try to trip you up and give you other units that you need to convert. So firstly, the units for the pressure have to be in pascals. And then for volume, we have to have meters cubed. And for the temperature, we have to have Kelvin. And this is called the ideal gas equation because normally no gases obey this exactly, but at room temperature and pressure, it holds quite well for many gases. And so a gas which obeys this equation perfectly is called an ideal gas. Also, one thing you need to know about the temperature is the conversion. So to convert from degrees Celsius to Kelvin, we have to add on 273, and we take away 273 if we want to convert from Kelvin to degrees Celsius. So now we're going to look at using the ideal gas equation. The first scenario in which we'll have to use it is when we're calculating the volume of a gas. And so, for example, if we had that the temperature was 293 Kelvin, the pressure was 100 kilopascals, and we had 1 mole of gas, then to find the volume, we would firstly have to write out the ideal gas equation that we know. So we have to memorize this. So we have PV is equal to nRT. And so we have to rearrange this to get V as a subject because we're trying to find the volume. And so we get V is equal to nRT over P. And that's because we've transferred the P over to the other side. And so now we just plug the numbers in. So we have V is equal to 1 times, and then R will be given to us. So this is 8.31 usually. And then we multiply by the temperature, which is 293. And then we divide by pressure. And now we need to remember that the pressure has to be measured in pascals. And so we have to convert this kilopascals to pascals. So we have to times it by 100. So I'm going to times it by 10 to the 3. So we have 100 times 10 to the power of 3. And so that gives us the pressure in pascals. So this gives us 0.0243. And now we need to remember that the volume of this, the volume used in this ideal gas equation is measured in meters cubed. So this will be in meters cubed. And so if we wanted it in decimeters cubed, then we'd have to multiply by 100. So we would get 24.3 decimeters cubed. And if we wanted it in centimeters cubed, then we would multiply it by 100 again. But I'm going to leave it in decimeters cubed. And this tells us that the volume of 1 mole of any gas at room temperature and pressure occupies 24 decimeters. And the second scenario we'll have to use the ideal gas equation is if we want to calculate the pressure of a gas. And this time we again use the ideal gas equation, but we rearrange it to get pressure as the subject. So we have PV is equal to nRT. And so rearranging this, we then have P is equal to nRT over V. Because this time we're swapping the P and the V, so we're taking the V to the other side. And then finally, we have calculating the number of moles of a gas. So again, we just rearrange the equation. So we have PV is equal to nRT. So this time we need N as the subject. So we have N is equal to PV, and then we take R and T over to the other side.